This video covers section 3.4, and in it we're going to learn another method of integration that's called partial fraction decomposition. And basically the idea is that if we were to have an integral of an ugly function like you see here in the introduction, so say it was x plus 3 over x squared minus 3x plus 2, and we couldn't use a u sub here because if we let u be the bottom, x squared minus 3x plus 2, then du is going to be 2x minus 3, and that's not what we have on the top. What we have on the top is x plus 3. So u substitution won't work, but if we could figure out how to decompose the fraction, if you will, and rewrite it as an equivalent expression, such as it turns out that x plus 3 over x squared minus 3x plus 2 is equivalent to what I just boxed here. It's equivalent to 5 over x minus 2 minus 4 over x minus 1. So the main thing that we're going to be talking about in this section is actually how we go ahead and decompose the fraction, or how we rewrite it like we see in the box here. And the reason why is because an integral like that is actually quite easy to find because it's a simple u substitution. So if we were to go ahead and look at example 1, or it's actually the warm-up solution here, there's really basically a little u sub we could do for each of these. So what I would do is go ahead and rewrite this integral. So I would say that this integral is equal to the integral of 5 over x minus 2 dx minus the integral of 4 over x minus 1 dx. And in fact, we could even put the constants out in front there. So I'm going to go ahead and do that. Instead of the 4 right there and the 5 right there, why don't we replace those with 1? So you have 1 over that. And then we can put the 4 out in front. That's a constant. And then the 5 for the first one. And then what you'll recognize is these look just like our natural log integrals, right? So we know that the integral of 1 over x dx is equal to the natural log of the absolute value of x plus c. So we're going to use that to our advantage. In the first one, what would we let u be? Well, yeah, u is going to be x minus 2. And in the second one, of course, in a similar fashion, we would let u equal x minus 1. And what's nice about both of these is that if du, or then du in this case is just going to be dx, and the same thing in the second one, it's just dx, because the derivative of x is 1. So what we end up with after we do the u substitution is we end up with 5 times the integral of 1 over u du minus 4 times the integral of 1 over u u. And so this ends up being 5 times the natural log of the absolute value of u minus 4 times the natural log of the absolute value of u plus c. Doing our back substitution here, we have 5 times the natural log of the absolute value of x minus 2 minus 4 times the natural log of the absolute value of x minus 1. And really, we don't even need to do that u substitution on, like, physically write it out. We can again do kind of a mental u sub. In fact, if I were to do a similar one, so let's say we had the integral of 5 over, say, 2x minus 1 dx, we know that we'd let u be the denominator, which means we're going to have when we take its derivative, we're going to end up with a 2, which is going to give you a factor of 1/2. So this is going to be the same as 5 halves times the natural log of 2x minus 1. So the 5 goes to the front, and then we get a factor of 1/2 because our u was 2x minus 1, and the derivative of 2x is 2. Okay, so that's kind of the idea. Because those integrals are so easy to find, that is kind of a motivator for why we want to go ahead and decompose the fraction, because we can go ahead and change our ugly fraction to look like something like that. So let's look at another example. Example 1 here is the first type of decomposition that we're going to deal with, and that's what we get when the numerator, so we have a rational expression. We have a polynomial on the top, p of x, divided by a polynomial on the bottom, q of x. And this is the case we're going to deal with when the numerator degree is higher than the degree of the denominator. And that's what we see in example 1, right? Because what's the degree in the numerator? Well, it's degree 3. And then on the bottom, we have degree 1. Remember, the degree is just the power, the highest power in that polynomial. So 3, of course, is greater than 1. So what do? Well, it says right there in the little discussion, it says when we have a rational function where the degree of the numerator is greater than the degree of the denominator, we're going to go ahead, or actually, so it's more than that. So when it is greater than or when they are the same, we simply use long division to rewrite the integrand in a form that is easier to evaluate. So long division, what does that look like with polynomials? This is hopefully something that you did in pre-calculus, but if you haven't, we're going to go ahead and review it now. And even if you did do it in pre-calculus, you probably did not spend a lot of time on it. So it's good to review anyway. So the top is what we're dividing x minus 1 into. So the top goes inside the box in the long division. And because there's no x squared term, we have to kind of put a ghost term there. So we'll just say plus 0x squared plus x, and we're going to divide into that x minus 1. And so it works much the same way we would do long division with numbers. We're going to take this first part of x minus 1, x, and we're going to ask, okay, well, what would you have to multiply x by to get x cubed? Well, that's going to be x squared, right? X times x squared gives you x cubed. And so then you multiply that back through both of these terms. We distribute it. So we say x squared times x is x cubed. And then we take also x squared times negative 1, which gives us negative x squared. And then what we want to do is subtract. So I'm going to do that in a different color here. We want to subtract these two terms. So x cubed minus x cubed, of course, that's going to cancel out. So that'll be 0x cubed. And then we have 0x squared minus a negative, which actually turns it positive. So this would be positive 1x squared. And then we're going to go ahead and bring down the next term. So we bring down the next term. When we do that, we have x squared plus x. And now we're going to go through this process again. So x into x squared means we need an extra x. And now we distribute again. So we say x times x is x squared. And then x times negative 1 is going to be negative x. And again, we're going to subtract. So we're going to subtract those two terms. And when we do that, we have x squared minus x squared. Again, those cancel, leaving 0. And then we have x minus a negative x, or x plus x, which gives us 2x. And again, we have a remainder, so we're going to add one more term here. Now there isn't a constant term, but we need to kind of artificially add that. We'll do a plus 0, and then we'll bring down that 0. So we bring it down. And when we do that, we'll go ahead and ask again, okay, so what does x need to be multiplied to get 2x? Well, it needs to be multiplied by 2. So distribute 2 times x is 2x, and 2 times negative 1 is negative 2. And then one last time here, we're going to subtract. And when we do that, we get, what, 2x minus 2x cancels, and then 0 minus a negative 2, we get positive 2. And that's our remainder. And that's as far as we can go. So we can go ahead and rewrite our integrand. So we now know that when we divide x squared plus x over x minus 1, we get the quotient x squared plus x plus 2 plus the remainder, which was 2, over the divisor, which was x minus 1. All right, so that's how we divided everything by x minus 1. That was the divisor, and there's a remainder of 2 left. And so now look at how nice that integral becomes. So our original integral was x cubed plus x over x minus 1 dx. We had no idea how to deal with that, but we now know that this integral is the same as the integral of x squared plus x plus 2 plus 2 over x minus 1. And that is pretty easy to evaluate because we can go ahead and use the power rule here. So this is 1/3 x cubed plus 1/2 x squared plus 2x plus we have a constant of 2, and this gets back to our warm-up, right? This is the natural log of the absolute value of x minus 1 plus c. And that really is all there is to these types of problems, one like this. So again, if the numerator is bigger than the denominator, we just use long division to divide. Don't forget, sometimes we have to add these ghost terms in, right? Sometimes we got to add if we're missing a term. And then we just rewrite our integral and evaluate. So in the next video, we'll look at some other types of scenarios that can happen, but this is the first type. Thank you very much.